Alright students, I'm going to review in-class exercise 1. So I will have review with most of you in class, but in case some of you might not have catch all the explanation, this might be a good juncture to review some of it. Okay, so for question 1a, you have electrical cables made out of copper wires. So describe the bonding. So as I mentioned, very often describe the bonding require a qualitative answers of some depth. So in this case, you need to draw a diagram as well, so with the aid of a labeled diagram, right? So in general, for a labeled diagram, some of you might be wondering how comprehensive should be the diagram. Like is this okay, like the one being shown as the sample scripts, or do I need to show like 9 circles, or is 4 by 4 okay, etc. So in general, the requirement is that it must be of a certain size. So I think 4 copper 2 should be fine. 6 would be, I would say, better. It looks neater given the space. If you just draw 2, maybe not so appropriate. Yeah, so you decide accordingly given the space provided. Yeah, but most importantly, you must ensure that the charges balanced. So because you drew 6 copper 2, so you just need to ensure that there are 12 electrons around it to balance the charge, to ensure that this particular snapshot you have taken, so-called you have taken in your mind on the huge metallic structure of copper, has a balance of plus and minus. Yep, and as I mentioned, in most cases copper 2 exists as copper 2, it loses 2 of its valence electrons to the C or the localized electrons. Yep, so occasionally you might be wondering whether I can have copper plus and copper 3 plus. Well, I mean, that is not impossible, but the system will balance itself out by converting the copper plus to copper 2 and copper 3 to copper 2, etc. So in general, we are looking at copper 2. Right, and then what are the kind of description required? So you are supposed to mention the kind of structure and bonding, right? So in this case, it's giant metallic lattice structure, so I think that needs to be mentioned. And the C of the localized electron is being contributed by copper atom. So in that case, the electrostatic forces of attraction is actually between the copper 2 cation and the C of the localized electrons. And this particular electrostatic forces of attraction, right, is being defined as metallic bonding. So you have to be very explicit here. You cannot simply just say electrostatic forces of attraction, because as I mentioned during the bonding lectures, all bondings are electrostatic in nature. Okay, so moving on to part B, we have copper wire surrounded by this material known as PVC, so polychloroethene. Some of you might be a little bit shocked. How come suddenly you have like a polymer here? Okay, so well, I mean, this is one of the Cambridge questions for A level, so I think a little bit of context is that back then the students learned a little bit about polymer, but for you guys, without knowing much about polymer, actually it doesn't really matter, because number one, you are given the structure. So this is PVC, polyvinyl chloride. In case you are wondering what exactly is vinyl chloride or what is chloroethene, right? So based on what you learned in secondary school, chloroethene looks like this. It's actually an ethene, but one of the H is replaced by chlorine. Yeah. So to form PVC, right, you might recall towards the end of secondary 4 that it undergoes what we call additional polymerization, which is radical based, and you form PVC. So there's a repeating unit of this C2H3Cl as exemplified here. Okay, yep. Then you also notice that there's no double bond. Yeah, so just all single bond throughout the whole structure. Yep. And then you were also told that electrical cable used in fire alarms are surrounded by magnesium oxide. Okay, so you're supposed to discuss why PVC and MgO are good insulators, or they can act as insulators. Yep. Magnesium oxide will be the easiest to explain, because that essentially is what you learn in secondary school, and it kind of appear everywhere in the lecture notes. Yeah, so basically in a solid state, the ions are held in fixed position by the very strong ionic bonding. So because the ions are not mobile, if you apply a potential difference, the ions are not going to move. Okay, so it's not going to move from high to low potential. So in that case, the strong ionic bonding holds the ions in a fixed position, so that prevents them from moving. Yeah, PVC explaining why PVC is a good insulator might be a little bit challenging, because you might be wondering, do you need to go and discuss the band theory? Some of you might read a little bit more to able to understand why certain materials are conducting. So for example, what's the difference between a conductor, a semiconductor, and a non-conductor? Yeah, for this question, the requirement is not to go into that kind of details lah. So all you need to do is simply just to focus on the covalent bonding within PVC. So that is all these covalent bonds. Okay, so I'm just going to highlight in pink. Yep. So all you need to do is just simply to emphasize that the bonding electron pair are held tightly by the two nucleus between the bonding electron pair is held between two nucleus. So for example, between carbon and hydrogen, is between the carbon and hydrogen nucleus. So basically, you just need to say that the bonding electron pair is held tightly by these two nucleus, and because of that, they are non-mobile. Yeah. Usually, if you want a covalent molecule, or rather a covalent macromolecule, to be able to conduct electricity, right, you need to have pi electron clouds that are conjugated. Okay, so I have introduced this new term to you, conjugated. It's not something you are familiar with. You're going to learn more about them under introductory organic chem, so you don't need to be too worried about it. Yeah, but a polymer with a conjugated electron clouds that is rigid tends to be conducting. Yeah, but in our case here, there's no pi electron cloud. They are all single bonds. Yeah, so therefore, being held in held strongly by the two nuclei holding the bonding electron pair, right? So the bonding electron pair is non-mobile, so no charge carriers, therefore non-conducting. Okay, so I think you can mention some of these ideas, and that will be more than fine. Okay, then for part 2, you're supposed to quote the bond energy, or CH. So just make sure you flip your data booklets, quotes the correct value. So that's 410 and 340. Okay, and then you're supposed to explain why they are different. Yeah, so the main idea that you need to highlight would be hydrogen is in period 1. Okay, so that means that it is going to use its 1s orbital, valence orbital, to overlap with the 2p orbital of carbon. And then for chlorine, it's in period 3, so it's going to use its 3p or 3s to overlap with that of carbon. Yeah, so if you look at how diffuse the valence orbitals are, right? So hydrogen being in 1s, right, is very compact. So that therefore the extent of valence orbital overlap between carbon and hydrogen is greater than that between carbon and chlorine, because chlorine period 3 valence orbitals are more diffuse, so the overlap will be poorer. Some of you actually ask, why can't I force the carbon and chlorine to be closer? So a simplistic explanation will be simply, if you try to bring carbon and chlorine closer, right, the inner quantum shell of chlorine will actually repel the carbon away. So there is a sweet spot for bonding to take place. Yeah, in order for the energy to be minimized. Yeah, then I think in the tutorial I also went on to talk about the 612 and potential energy diagram. So I think I can just give a very simplistic view. So if I have energy, and then I have distance. So this is actually the distance between the nucleus. So distance between nucleus, two atoms. Okay, so let's say this is the sweet spot, what we call the bond length. So this is the bond length, let's call it x. Okay, I'll just call it x over here. Yep. So this bond length will be one where it has the lowest energy level, because that is the optimal distance. Yeah. So so this will be this will look something like Cl, for example. Yeah. Then if I try to pull the Cl away, right, then its energy will go up. Okay, or become less negative, because it is less stable. Okay, or because less heat is given out. And then so much so that if you pull them very, very far apart, yeah, then essentially there is no interaction. Yeah, so it will tend towards 0. Yeah, but if I try to force the chlorine and carbon to be even closer to each other, right, the energy over here will go up. Yeah, because electronic repulsion or repulsion between the nucleus become a more significant forces. So in that case, it's going to destabilize the system, and so much so that you just go all the way up. Yeah, so this is sort of known as the 612 energy potential curve. So those of you doing physics, you will learn that. Yeah, so I think those of you doing physics, you just draw it as like this, something like that. Yeah, so it's actually quite similar to what you learned. Yeah, so if you're interested, you can read more about it. Just take note that what I'm presenting here is just a very simplistic view. May not be 100% very accurate, or even for the labeling, but I think it helps in a little bit of understanding, or a bit of understanding on why the two atoms cannot come infinitely close. Okay, and then moving on to part C, when magnesium is burnt in air, a mixture containing MgO and the magnesium nitride is formed. So magnesium nitride is an ionic compound. You were already told that it's an ionic compound, so there's no debate about it. So the dot and cross, if you recall from the lecture, magnesium having lost its 2 valence electrons, you shouldn't be drawing the valence electrons from the second principal quantum shell. So you just leave it empty, like what is being illustrated here. And then for nitride, it gains 3 electrons. So this is the representation. Yeah, and the number of moles of Mg2 plus and N3 minus must match in such a way that the overall charge is 0. Yeah, but anyway, it's given here, so it's 3 and 2. So I think you can just put the coefficient as 3 and 2. Yep. And then the next question is suggest why the melting point of magnesium nitride is higher compared to that of magnesium oxide. Yeah, so a very important relationship you need to cite over here is the lattice energy, directly proportional to the product of the charges, and inversely proportional to the sum of the ionic radii, or the interionic distance. Yeah, you notice that for nitride, it has a higher charge as compared to oxides, so the product of the charges for magnesium nitride will exceed that of the product of the charges of magnesium oxide. However, nitride is actually a bigger anion as compared to oxides. So in the case of the sum of the ionic distances, magnesium nitride will be greater than that of magnesium oxide. Yeah, so you notice that if you simply look at the numerator, magnesium nitride will win, so-called, will have a more, will have a lattice energy of a greater magnitude. But if you simply look at the denominator, then magnesium oxide will be the one with a larger magnitude. So in the end, how do we decide? Actually, we do not really need to decide, because the question already decided for us over here. Yeah, so magnesium oxide has a higher melting point. So in that case, your conclusion must be focusing on the fact that magnesium nitride's lattice energy is numerically larger or more exothermic. So in order to focus on that, you kind of have to conclude, so-called conclude, that therefore in most cases, in fact in all cases, the product of the charges, or the numerator, is a more important factor as compared to the sum of the ionic radii. That is the denominator. Yeah, so if you have that conclusion, then you will be able to mention that because of that, the lattice energy of magnesium nitride is more negative or numerically larger, and therefore I will need more energy to overcome the stronger ionic bonding. Yep, so that's about it, and we'll see you in the next review to probably in class exercise 2.